Okay, in this video, I'm going to start talking about one of the most important things in IB physics that will stick with you for the entire two-year course, and that's the idea of errors and uncertainties. Now, I talked a little bit in class about, I've talked from time to time about how we can never measure anything exactly. Okay, it might seem kind of depressing, but it's true. So no matter how high-tech or how expensive or how careful we are measuring something, we can never ever measure something without some degree of error. And the way that we quantify the error is with these things called uncertainties. Now, if you were in my class last year, we've already talked about error bars on graphs, okay? Well, error bars, that's just a way of quantifying the error. And in fact, error bars are thought of as uncertainties. Now, I talk in class about errors and uncertainties and errors and so forth. I may use them interchangeably, but really they're quite different, and I'm going to talk about that in just a minute, okay? So no matter how hard we try to control things, some level of experimental error is unavoidable, okay? And the source of error may be one of many things. It may be just one thing, or it may be sort of compounded by lots of different things. Nevertheless, no measuring instrument is perfect, and the way that we report experimental results with appropriate uncertainty and following through, especially in calculations, is a critical part of the IB sciences, okay? So over here on the right, a couple of examples of how we measure things. I'm going to teach you guys how to do also dealing with to deal with digital devices and what we do with those. And I should also tell you that when you get to university, you may very well, if you decide to stick with science, you may very well end up learning a new way of dealing with errors and uncertainties. There's lots of different ways to deal with it. So the way that we deal with it in the IB is seen as rigorous enough to sort of hold up in a college or university or a professional research atmosphere, but at the same time it's not mathematically too complicated for you at the high school level. So personally, I think it's a really good way to kind of balance those, but it's still a real way to do errors and uncertainties, and it's completely valid mathematically and scientifically. Okay, so the first thing I want to do then is talk about exactly what I mean by an error. And an error, scientifically speaking, is the difference between the measured value and the expected value of something. It's not that you're making a mistake, it's that there is an error. Okay, so again, in common language, error might mean a mistake, right? But in science, it does not. And errors are unavoidable when you're taking data. Okay, an uncertainty is simply the way that we quantify or summarize the error. That's the plus or minus that you guys are used to. Also, uncertainties are unavoidable. Now, these two things are not the same as mistakes. A mistake is a matter of simply just not doing something correctly. You're careless. Either your friends are bugging you, or you're distracted, or you're really tired because you were up late last night, or you're hungry, or whatever. These are avoidable. We can avoid mistakes. So I cannot reiterate enough how important it is that errors are not the same as uncertainties, although both are unavoidable, and neither of them is the same as a mistake. Okay? Now, again, we often use them in common language to mean the same thing, but they're not. You'll never be penalized for reporting and treating errors and uncertainties correctly. However, you will be penalized for making mistakes, and it will be very obvious to me when I'm reading your lab reports whether you made a mistake, whether you were careless, or just used the wrong procedure, okay? However, there are some cases where mistakes come out in your data, especially with graphs, and you won't be penalized if you address them and justify them, and in many cases, especially with graphs, you will end up throwing out mistakes, and as long as you mention that, you're not going to be penalized for that. So overall, our strategy in dealing with these things, errors and uncertainties, we want to minimize them, knowing that we can never get rid of them, but at the same time, we have to be super honest by reporting them truthfully. Very, very important part of your scientific integrity as a physicist, okay? Okay, so I want to talk about two other terms that tend to get really confused in common language, and that is accuracy and precision. So when we talk about accuracy in science, what we're talking about is the agreement between your measured value and the actual true value or accepted value of what it should be. Okay? This is quite different than precision. Now, precision refers to the degree of consistency and agreement amongst measurements of the same quantity. So it's how reproducible your result is. So for example, if you took 3 trials of something, if you measured something 3 times and you got very close to the same amount of whatever that is every single time, your data would be very precise. You cannot say your data is accurate unless you actually know the real value of the thing you were trying to measure. Does that make sense? I'll give you some more examples in just a little bit. So accuracy is really about giving true readings, okay? And precision is about detail. So you hear me say in class about the precision of an instrument. Well, that's how much detail there is. I say precision when I talk about the smaller the least count is, the more precise the instrument is, okay? It would not make sense to say that an instrument is accurate. That doesn't mean anything unless you're measuring something with it. And even then, you would talk about the reading that you're getting from the instrument as being accurate, not the actual instrument itself. So just make sure that you understand the difference between these two, okay? Another way to think about it is like this. If you've ever played darts, a really, really fun game, okay? It takes a lot of practice, all right? We have 4 different scenarios here. Obviously, we're trying to get to the bullseye. We have 4 darts, and we want all 4 shots to hit the bullseye, okay? In the first case here, they're kind of spread out, and none of them are super close. I guess this one's kind of close to the bullseye, but generally they're kind of all over the place. This is not accurate, and it's not precise. This is kind of the worst case scenario, so it gets a sad face, all right? The next 2 cases, in this one, generally speaking, the 4 darts are closer to the bullseye, but they're pretty far apart, okay? So your shot was not reproducible, okay? So that's accurate, more accurate, but not precise. It gets kind of a medium face. In this case, your grouping, we call it grouping in darts. Your grouping was really good, so it was precise, but your grouping was really far off the mark. So we say that's not accurate, but it's precise, and that's, okay. The 4th case, this is what we want. We want all 4 darts to be really accurate. And when I say all 4, I really am talking about the precision. We want each throw that you make to be reproducible from the last, with the last, okay? That's accurate and precise, and it gets a star and a smiley face. So again, not accurate, not precise, case 1. Case 2, accurate and not precise. Case 3, not accurate but precise, and what we want is accurate and precise with a smile and a star. That's what we're always looking for. And you can control these things if you're really careful, and if you know what you're doing and you're using good instruments, you can control accuracy and precision, okay? Okay, so again, if you imagine if you measured the same thing many, many times. If you and your instruments were perfect, every single measurement would be exactly the same. That never happens, or very rarely ever happens, okay? Now, in some cases you've measured things and you actually did get the same measurement each time. That's because generally the least count of your device is not small enough to detect those errors. And we have ways of dealing with that, which I've talked about in class and I'll talk about in the future. So the reality of your data is that you end up with this thing called the normal distribution. And if you study statistics and mathematics, you may have heard this term normal distribution, okay? The area under this curve between any 2 measured values gives the number of measurements in that range of values. And what I mean is this, okay? On the y-axis, you have the number of measurements of something. Let's say you're measuring something. Number of measurements, okay? And on the x-axis is the actual value that you measured. The dotted line would refer to the actual true value of what you're trying to measure, okay? Now, if you're really careful and if you're using good instruments, you're going to end up, hopefully, with the highest number of measurements being the actual true value of what it is you're trying to measure, right? Okay? And what you'll find statistically is that this curve, the number of measurements, drops off as you get farther away from the true value if you're a good scientist and if you have a good apparatus. Now, statistically, from this particular diagram, it looks like you would never have a measure that's this far off over here because the number of measurements is on the y-axis is 0, okay? So the best case scenario would be if you have a very tight curve like this, a bell curve we call it, like that, okay, around the true measured value, it means your data is precise and it's accurate, okay? If you have a very tight bell curve, say over here, way over there, at a value that's not really the true value, well, guess what? Your data is precise, but it's not accurate. So we're always striving for a very tight bell curve centered on the actual true value of what it is we're trying to measure, okay? And the bell curve also gives you a degree of the accuracy and precision. So for example, if the curve is kind of flat and kind of spread out, okay, but it's fairly close to the true value, which is right here, we say that it's pretty accurate, but it's got low precision because the bell curve is flat and spread out, meaning that the trials were not very reproducible. On the other hand, we could have, like I said, we could have a tight bell curve here that's very tight around a measured value, which is highly precise, but if the true value is way over here, then it's not very accurate. Okay, so again, we're looking for a tight curve centered around the actual true value of what it is we're trying to measure. Okay, all right, so let's do a couple of examples. These are past IB past paper questions, paper ones. Okay, so an ammeter measures the electric current through a circuit, and it has a zero offset error, meaning when you go to zero it, there's no current, it's not actually reading zero. It may be reading like 0.025 amps or something like that. Okay, so this fault will affect what? What do you think? Okay, it's gonna affect the accuracy of the readings, meaning you could take lots of different readings of the current through this circuit, and you could get the same value. It's called a systematic error, but it would only affect the accuracy, right? Not the precision, because precision refers to how close all your values are together. Okay, try this one. Pause the video and read this past paper question from paper 1. Okay, so this student used a voltmeter to measure potential difference. You guys will do that in this class someday. Okay, and the student gets these 4 different readings. Okay, the student averages the readings, but doesn't take into account a zero error on the voltmeter, which is what I just talked about before, a zero error. Okay, so what's this going to be? This data looks pretty precise, right? Okay, the average measurement of the potential difference is which of the following? Okay, it's going to be precise, but not very accurate. Okay? Okay, so we have 2 different types of errors in measured data. Okay, random and systematic. And I've referred already to systematic errors, and I'm going to show you guys what random errors are. These are 2 very different kinds of errors, and if you pay attention to things, you can always deduce which is which in your data. Okay, a random error is a completely random fluctuation, as the word implies. It's totally random, and it can be due to a couple of things. The readability of the instrument. Maybe your instrument is old and it's just not functioning very well. Okay, the effects of something changing in the surroundings between measurements. For example, you do trial 2 and 3 are maybe at a different temperature for whatever you're measuring, or the observer being less than perfect, and we're all less than perfect to some degree. Okay, a systematic error, on the other hand, these are errors that are reproducible. Okay, now the most common reason for systematic errors are instruments being wrongly calibrated, like a zero instrument error. Okay, or just wrongly calibrated in general. All of the values are for some reason off, right? Okay, or the observer being less than perfect in the same way during each measurement. Does that make sense? So usually when you make when you have an error, you're doing something, you're being less than perfect. You're not lining up your eye just right or whatever. Usually that sort of less than perfection is random. But if you're less than perfect in the same way every time, then that means that will result in what's called a systematic error. Okay, and I'll show you how to identify these types of errors. Random errors can be reduced by averaging. Okay, so taking lots of trials and taking the average. So that's why we take lots of trials in science. The more trials, the better. A precise experiment has a small random error. Okay. Now, systematic errors can't be detected or reduced by taking more measurements, but there are easy ways to detect them if you graph, and I'll show you how to do that. So an accurate experiment has a small systematic error. Okay. So again, how do you see immediately if you're dealing with a random or systematic error? Okay, if you're graphing, if you're taking data that is that you know to be linear, okay, or you suspect to be linear, okay, and it is linear, but it doesn't go through the origin, for example, and you know that those 2 things you suspect they're proportional, this y variable offset would be the systematic error. So every single value along that dotted line with triangles, those are all off by the same amount. Okay. Now all the x's, you see how it kind of doesn't really line up. They're kind of all over the place. Those would be more indicative of random errors. Okay. Another example, example 3. Go ahead and pause and read this past paper question. Okay, so we're saying that in the measurement of a particular quantity, there are random and systematic errors. Man, and that's the reality in pretty much all the things you measure in this class. What changes would repeated measurements of this quantity have on the random and systematic errors? Well, I just told you that systematic errors would be unchanged, right? Although you would detect them if you were to graph them, and random errors would be reduced. But again, we can never ever get rid of them completely. Okay, so most people don't really know how to report a single measurement. So I'm going to teach you guys how to do that. I've talked about this a little bit last year and this year. But I'm going to really go through it in detail with you now because I want to make sure you know how to do this, okay? So generally what we do is we report the measured value with the precision not going beyond the least count on the instrument. In cases where the least counts are wide enough to estimate beyond them with certainty, you are free to do that. It's no problem. It's completely up to you, but don't overestimate the precision of the instrument. Most people try to overestimate the precision of their instruments with terrible results. Now, some people say, you'll read this in some literature, especially some IB books, they'll say that uncertainty should be 1/2 the least count. This is technically correct, but because uncertainty should be reported with the same number of decimal places as the instrument, it's always going to be the same as the least count because you're going to round it up anyway, and I'll show you what I mean. Okay, so instrument uncertainty should be restated as plus or minus the least count and match the number of decimal places of the reported measurement all the time, every time you measure something. And they should only have one significant figure if possible, okay? If the number of decimal places in your uncertainty does not match the measurement, you got to round your uncertainty up so it does, and you always round it up. You never round it down. I'll show you some examples of that, okay? All right. First thing we're going to measure together is the length of this very cute little teddy bear, okay? Now, if this is the centimeter rule here, okay, all right, this is 1 centimeter, this is 2 centimeters, this is 3 centimeters. You can see that the length of this teddy bear is 1.2 centimeters. Now, because we report our uncertainty as plus or minus the least count, this is going to be plus or minus 0.1 centimeters, which is obviously 1 millimeter. So I think we're all cool with that. I think that's what you guys would probably do in this case. Now, if the uncertainty were 1/2 the least count, as sometimes which is technically better, then you would report it as 1.2 plus or minus 0.05 centimeters. But that is like a cardinal sin in experimental science in the IB, because this is a precision mismatch, and I will take points off every lab you ever do this. Even if you do it once, you're going to lose points. It's so important. You would round the 0.05 up to 0.1 anyway. So in effect, in practice, you can use half the least count, but in practice, you're going to always round it up to be the least count. Does that make sense? And you can make this argument for anything you measure with any instrument. Another way of thinking about it, if we use half the least count, and we're measuring with this particular device, there are 2 ends to measure. So wouldn't the uncertainty be 2 times the half the least count anyway, which is just the least count? Does that make sense? So that would be 1.2 plus or minus 0.1 centimeters. Now, if you think you can estimate beyond the least count, then you need more decimal places, okay? And you can use half the least count. However, there are still 2 ends in this case. So really it'd be 0.122, for example, if you think it's 1.22, for example, okay? You would actually report it as plus or minus 1.10 instead of 0.05 because there are 2 ends to measure. Does that make sense? Okay. Now if you put 1.22 plus or minus 0.05 centimeters, I'm not going to take off a point for that, but it's really technically not correct. Notice how, in this case, I have 2 significant figures in my uncertainty, so that kind of violates that rule that I said you should do if possible. Not really a rule. If you can do 1 significant figure, that's great. Or really, it's better to say if you can do 1 non-zero digit, that's usually what you should do in your uncertainty. And that's just kind of what scientists do all over the world. That's good form scientifically.